Another kind of example that will give us an opportunity to review implicit differentiation is the following. We want to find the rate of change of y with respect to x along the curve of equation natural log of xy equal y sine x. So we proceed by implicit differentiation. That is, we're going to differentiate with respect to x both sides of the equation of the curve, considering y as a function of x. So in doing so, when I differentiate the left-hand side, I'm going to have log of some function that I differentiate with respect to x. So I'm going to get 1 over this function, in other words 1 over xy, multiplied by the derivative of xy. So that's what I get on the left-hand side. On the right-hand side, I have a product of the function y with the function sine x, and I differentiate that with respect to x. So I use the product rule. Derivative of the first factor y just gives me this derivative of y, dy over dx, that I multiply by the second factor unchanged, just sine x. Then I have y multiplied by the derivative of sine x, which is cosine x. What remains to be calculated is on the left-hand side the derivative of the product xy. That's a product, so we use the product rule. When I differentiate the first factor x with respect to x, I get 1. So that's why the first term in the parentheses is y. And then I add the first factor unchanged, x, multiplied by the derivative of the second factor, which is just dy over dx. Now what we want to do is solve in this equation for dy over dx. And to do that, we're going to put together all the terms that contain dy over dx and factor out dy over dx, and then all the terms that do not contain dy over dx on the other side of the equation. So this is what we obtain. And to see that, note that this 1 over y dy over dx comes from the product of these two terms. You see that when I multiply things through, the x dy over dx is going to cancel with the x at the bottom of 1 over xy, and we obtain 1 over y dy over dx. This negative sine x dy over dx comes from sine x times dy over dx on the right-hand side of the equation. If I bring it back on the left-hand side and then factor out dy over dx, I get this 1 over y minus sine x. Then the terms that do not contain dy over dx is y cosine x that is already on the right-hand side. And then there's also 1 over xy multiplied by y. The y cancels out, that gives me 1 over x, but it's on the left-hand side, so when I get it to the right-hand side, it's negative 1 over x. Now, in order to divide both sides by the factor in front of dy over dx, I'm going to first write them as one fraction. In other words, I want to write the sine x as something over y. So I will have to write that as 1 minus y multiplied by sine x, all of this divided by y. And I'll proceed similarly on the right-hand side because it's going to be easier to write things after that. So if I write everything with denominator x, I get xy cosine x minus 1, all this divided by x. Now I can multiply both sides by the reciprocal of the term in front of dy dx. In other words, I multiply both sides by y divided by 1 minus y sine x, and this is what we obtain. Xy squared cosine x minus y divided by x minus xy sine x. Now let's turn to some integrals. We've seen that the integral of dx over x is natural log of absolute value of x, up to some constant, of course. Let's see what that means on some examples. Starting with the integral from 1 to 2 of 4 plus u squared over u cubed. Well, we can rewrite that as 4 over u cubed, or 4u to the negative 3, plus u squared over u cubed, which is just 1 over u. Now it's easy to find an antiderivative of this function, because u to the negative 3 has as an antiderivative u to the negative 2 over negative 2. So that gives us, when we multiply by 4, negative 2 over u squared. And then we just have seen that an antiderivative of 1 over u is natural log of absolute value of u on any interval that does not contain 0. Since we're looking at the interval 1, 2, there is no problem. So now we have an antiderivative of our function. We're going to plug in the bounds of integration. We plug the value at 2, gives us negative 1/2 plus ln of 2, and then we subtract the value at 1, which is simply negative 2. So we have 2 minus 1/2 is 3/2 plus ln of 2. The second example is the integral from e to 6 of dx over x ln of x. Remember that e here is the Euler number, which is defined by the fact that when plugged in the natural log, it returns 1. Now here we're going to proceed by substitution, because we observe that if u is ln of x, and du is dx over x. In other words, we have inside the integral du, dx over x, and then u at the bottom. In other words, the integral from e to 6 of 1 over x ln of x is really just the integral of du over u for u equal ln of x. And because we're using substitution in a definite integral, we also have to change the bounds of integration. And to do that, remember that to obtain this bound, for instance, you look at the fact that x is in the interval from e to 6. So what does that mean for u? If x is e, then u is ln of e. I plug x equally in this, and I obtain ln of e. Proceeding the same way for the upper bound of integration, we get ln of 6 for the upper bound. And note that ln of e, that is circled here, is really nothing but 1 by definition of the Euler number e. So we obtain an antiderivative of 1 over u, which is natural log of absolute value of u, that we're going to evaluate between 1 and ln of 6. The value at ln of 6 is just natural log of 6, and ln of 1 is 0, so we obtain simply natural log of 6 for this integral. Moving on to the third example, which is now an indefinite integral, we are looking for an antiderivative of cosine x divided by 2 plus sine x. Again, we're going to proceed by substitution, observing that if u is 2 plus sine x, then du, the derivative of 2, which is 0, plus derivative of sine x, which is cosine x. So du is cosine x dx, which is exactly what we have on top. So we have du divided by u. So using this substitution, we rewrite our integral as the integral of du over u, and an antiderivative of 1 over u is natural log of absolute value of u. So that's what we obtain up to some constant. Rewriting what u is, it's 2 plus sine x that we have under an absolute value. But in this case, we can drop the absolute value because sine x is between negative 1 and 1. And therefore, when we add 2, we get something that is always positive, so we can drop the absolute value. And to conclude this section, we can apply what we have seen to finding a formula for the integral of tangent x, which was a missing formula in Calculus 1. So when I integrate tangent x, I'm really integrating sine x divided by cosine x. And under that form, you see that if we take for u cosine x, then du is really just negative sine x dx, because the derivative of cosine x is negative sine x. That means that at the top we have negative du, and at the bottom we have u. In other words, our integral can be written as the opposite of the integral of du over u, and an antiderivative of du over u is just natural log of absolute value of u, up to some constant. One of the properties of the natural log is that if I have a multiplicative constant in front, I can bring it in as a power, so I get natural log of absolute value of u to the negative 1, which I can write natural log of absolute value of 1 over u, all this up to a constant. Going back to what u was in terms of x, I get natural log of absolute value of 1 over cosine x, but that is absolute value of secant x. So that gives us a formula that the antiderivative of tangent x is given by natural log of absolute value of secant x, and that is of course up to some constant. Now, with what you have seen so far, you can go ahead with the first homework set on the natural log function.